Hello guys, welcome. In today's video, I'm going to talk about how to use multiple channels of the ADC using DMA and interrupts. Roughly speaking, DMA, direct message addressing, is a way of doing certain operations like ADC, I2C, USART, etc. without using the CPU. And that can be very interesting if you have a lot of data to process. Now I'm going to select two channels in single-ended mode. And here you have the parameter settings. So for this, I'm going to leave 12-bit resolution. And I want to enable scan conversion mode so that I can use multiple channels. But as you can see right now, I cannot do that because I need to create the DMA first. So here I'm going to go here, add a DMA. Since I'm already in the ADC section, that's the only choice I have. And here you have the DMA. For the data width, it really depends. You can have 8-bit, 16-bit, or 32-bit. Since I'm using my ADC is 12-bit, I'm going to stay with the half word, 16 bits. And another thing, I'm going to make that buffer circular. This allows me to get updated values because if I leave it as normal, I'll only have one conversion, and then after that, it won't be updated because the buffer won't be overwritten. So I have to make it circular if I want my values to be continuously updated. And here, since I'm going to use also interrupts, I'm going to check this box. But if you're just going to use DMA, only this one. Now here you have the scan conversion is still disabled because I just created the DMA, but I have to enable it, and the number of conversion which is going to be correlated to the number of channels. So here I'm using 2 channels, so I'm going to do number of conversion 2, and automatically it's going to get, as soon as you increase the value, it will automatically go into enable. And here I'm going to choose continuous conversion mode, and DMA continuous request is also going to be enabled. We're going to see the effects of leaving that enabled during the debugging. So for the rest, end of single conversion, overrun data written, everything I'm going to leave it it's normal. But here, for example, I'm going to use end of sequence of conversion since I'm using multiple channels. Now, if you go down here at rank, that's where we're going to choose which channel is going to be, which channel we're going to use. So for this one, we're going to leave it at channel 1 corresponding to this one. And for the second, we're going to choose channel 2. Now, another very important thing is the sampling time. Depending on the impedance of what you're measuring, you may need more time. So these cycles depends on the ADC clock. So here, for what I'm going to do, I'm going to choose something that's roughly 19.5 cycles. It's going to do the job. But if you are using ADC and you see that the values are not really what you expect, consider increasing the number of cycles. So I'm going to leave the rest like that. So that's it for the ADC, including DMA. And now, since I'm going to use also interrupts here, I'm going to get into my timer. So I'm using like my clock configuration. Everything is at 8 megahertz. And this corresponds to 1 hertz frequency. I'm not gonna get too much into details of how to make a timer here, because I already talked a lot about that in my previous video that you can find in the description if you're interested. Now here in our code, this is our timer using timer tree, the ADC DMA handle, the regular ADC handle. Here I have these variables. So this is going to be my buffer containing the two channels, the two values. Here I have another variable here for my photoresistance, and this is just another thing for some voltage that I'm going to be using. And this is a counter that I'm just going to put in my while loop to check what's going on, if my CPU is running or not. And here are my callback functions, the period elapsed callback, that will be called every time my timer is going to reach an overflow. And this is the HAL ADC conversion callback function that is called every time the buffer is filled. So every time the conversion is completed by the ADC. So I have this HAL team base that interrupt for my period elapsed callback function, and this is for the DMA. And here I have this little code with my counter just to check what's going on in the while loop. And here is going to be the condition I'm going to use. So if the voltage is under this value and my photoresistance is under this value, I'm going to turn on the LED. And here is our period elapsed callback, but I'm not going to use that right now. I'm just going to show you something before that. And here in my HAL ADC conversion callback function, that's why I do the conversion. So I have my reference voltage of 3.3 volts and my 12-bit timer, so the maximum value being 4095. And I'm converting the two values. And as soon as I've done that, I'm going to stop the DMA. Here you have the continuous conversion mode enable and DMA continuous request enable. Those two things pretty much do the same thing. This just means that for the continuous conversion mode that your ADC is going to continuously convert values, and this means that your DMA is going to continuously push values in the buffer. Now the thing is, if you disable this one, it means that the conversion will happen only one time. Or if you disable this one, it means that the request, the DMA, is going to happen only one time. So it works a little bit like a logic AND. So if you want your continuous conversion, your values to be continuously updated, you have to have both of them enabled. But if you want it to be disabled, you can just have only one of them disabled because the end result is going to be the same, whether you disable this one or this one. So you can disable both or just one of them. So right now I'm going to launch the debugging. Let's start the debugging. So here I have my converted values, and inside the buffer I have the raw values coming from my ADC. Let's start. Now, as you can see here, nothing is happening in my CPU. I mean, it just did one here. No values are converted, and this thing is running. Now, the other one is because I have a potentiometer. So I'm at 0, and now I'm turning it a little bit to increase the values. And you can see that the DMA itself, the conversion, is working really well. And I have continuously, I mean, the values are constantly updated, and it's going very, very fast. And that's a problem. The thing is, this in the callback function and this are operations that are made by the CPU. But the fact that the DMA is constantly relaunching, the ADC is happening all the time, and I only have two values in my buffer. That's very small for DMA. So the thing is, it's constantly working, and my CPU is not able to follow. That's too fast for for my CPU. So I end up in a situation where nothing else than the DMA is actually working in my code. Now I'm gonna just disable, like I said, I can just disable one of them, and we're gonna see the difference. So now, as you can see, I have nothing happening. Like the DMA is stopped, and but I did had one conversion, and you can see the counter. Like my CPU is not blocked right now. It's doing its thing, but I mean, I'm not I cannot do anything with just one values, even if I turn the potentiometer, and that's not a configuration that I'm interested in using. So what I'm gonna do is I'll go in my interrupt, in my callback function, and I'm gonna manually restart the DMA. So every time I'm gonna reach an overflow, I'm gonna restart my DMA. So right here you can see my CPU is working, my photoresistor is moving. If I put my finger, I am in that condition where my voltage is lower than 2400 and my photoresistor is lower than 50. And if I increase the value of my voltage, so you can clearly see that right now I have something that's working and is not blocking my CPU. Now let's change the value of our timer and make it very fast. So right now I am at 100 kilohertz, and let's see how our system behaves. And as you can see here at 100 kilohertz, we're not entering the while loop. We only had one conversion happening. Even the DMA is not working. And it's like it did the single conversion thing and it stopped. But it's not supposed to do that. And the problem is because this 100 kilohertz is too fast. And it's just messing things up. And let's decrease the speed a little bit and see what happens. Now at 100 hertz, you can see that I have my DMA working. I can even have my values are converted, but nothing is happening in the while loop. And I have this conversion happening here because it's inside the callback function. And the callback function has a higher priority than whatever is happening in our while loop. And as a result, the small amount of time that the CPU has, it's going to dedicate all that into the callback function. And since it doesn't have enough time to deal with the callback function and with our while loop, the thing is, as you can see here, my LED is not turning on. So the while loop is definitely not working. But because the callback function has a higher priority, the CPU is at least able to do the conversion. So let's lower the speed again in the timer and be at 1 kilohertz. And now we have everything working because I've lowered the speed of our timer. and everything is working fine. So at the end of the day, it's all about timing. So if you are doing your ADC at a speed that your CPU cannot handle, you will be in a situation where you will only have DMA, but the rest of your code is going to be blocked. So you have to really take that into consideration depending on what you're doing. And you can always go in the clock configuration and adapt things in a way that you'll be able to use your microcontroller to its full potential. This is it for today's video. I hope you've learned a few things and see you soon. Stay tuned.